One of the things we've learned in this module is that an acid-base reaction is essentially a proton transfer process. I want to look at that as in a more global way in this video and see if we can understand something about what drives that proton to go from one species to another. So our learning goals are going to be how to find out the outcome of proton transfer between two compounds, and then how we might use pKa tables to actually predict the direction and the equilibrium constant for that process. So here is a typical proton transfer process between a base and an acid. So in the past we've been looking at equilibria that involve each of these with water, and we're going to use that in this particular video. But right now what we're interested in is a reaction where a base reacts directly with an acid. A proton then moves from the acid to the base to give a protonated base and the conjugate base of the acid. So this reaction, when you think about it, is really just a competition between two bases, one of them being the original base, B, and the other being the conjugate base of the acid, A-. And they're competing for a proton. So we can think of it almost like a little tug of war. And that proton is going to decide to go one direction or the other. And the equilibrium constant of this reaction that we've drawn up at the top is going to tell us who the winner is. So now what we want to do is we want to consider the base equilibria that relate to both the conjugate base of the weak acid, A-, and to the base. And we're going to test how strong they are versus water, and that's going to tell us how strong they are relative to one another. So here is the Kb reaction for the conjugate base of the weak acid. And here's the Kb reaction for the base in this overall reaction. Now I want to combine these in a way that are going to give me the ultimate, give me the reaction that I'm interested in, because I'm interested in finding out what the equilibrium constant is for that. Now I notice that in that equilibrium drawn at the top of the page, I've got BH plus and A minus on the right hand side. And in the two equations that I've drawn down here, BH plus is on the right-hand side, but A minus is on the left-hand side. So I'm going to need to reverse that reaction if I want to add these together and get a net reaction that's the same. So let me reverse that reaction. There we go. Now notice a couple things changed. I mean, what were on the product side now are on the reactant side, but I had to change the equilibrium constant, because when we reverse a reaction, remember, we get the new equilibrium constant is 1 over the old one. So now my equilibrium constant is 1 over the Kb for A minus. Now I want to add these together, but I notice that I have hydroxide ion and water on both sides of these equations as I add them together, so I can actually eliminate them before I add them together. And now when I sum the two equations, I'll end up with the equation that I'm interested in. So great, I figured out a way to get to that equation using two equations whose equilibrium constants I either know or can find out. Now what about the equilibrium constant for this reaction? Well, remember, when we add two reactions together, the resulting equilibrium constant is the product of those two equilibrium constants. So when I multiply them together, I'm going to end up with an equilibrium constant that's equal to the ratio of the two Kb values. In this case, it's going to be Kb of B divided by Kb of A minus. Now, this has a certain nice symmetry to it, because we're discussing this reaction as though it's the competition between two bases. And now we find that the equilibrium constant, in fact, is just the ratio of their two Kb constants. Well, let's follow this a little bit further. So here is the reaction again, and here is our result for the equilibrium constant. Let's analyze this and see if we can't understand a little better what's going on in this reaction. Well, we know that the larger of the two Kb's is going to be the stronger base. Okay, the strength of the base sort of tracks with the value of Kb. So we have two possibilities here. Now, the first possibility is that the Kb of B is greater than the Kb of A minus. All right, now Kb happens to be a strong base in this case. It's stronger than A minus, but it also happens to be in the numerator of our expression for Keq. So if it's bigger than Kb of A minus, that means the equilibrium constant's got to be greater than 1. And when the equilibrium constant is greater than 1, it favors the right-hand side of the equation, which means products will be favored in this case. So we should expect to see the proton end up with B, not with A. Now the other possibility is that Kb of A minus is greater than the Kb of B. This tells us that A minus is the stronger base. Since it's in the denominator of the expression for the equilibrium constant, we should expect the equilibrium constant to be less than 1. And whenever the equilibrium constant is less than 1, it's the left-hand side of the equation that's going to predominate, so the reactants are favored in this case. Now, this is all fine and good, but one problem is that Kb values, some Kb values are tabulated and known, but frankly, not nearly as many of them as there are of Ka values. For whatever reason, the preference has fallen to Ka values. So what we want to do is we want to figure out a way to use Ka as our indicator of the transfer rather than Kb. Well, I'll remind you that for a conjugate pair, that is A minus and HA, or could be for B and BH plus, the product of Ka and Kb for that conjugate pair always equals Kw. So that means I could write the Kb for A minus is just equal to Kw over the Ka for HA. So now if I do this for both the weak acid and its conjugate base, we do it for A minus, we can also do it for B. That means I can now express the equilibrium constant purely in terms of Ka values. So what that looks like is this. So just remind you, Kb was equal to, K equilibrium was equal to Kb of B over Kb of A minus. And now when I make this substitution of each of those for Kw over their respective Ka values, that's going to flip them over. So the Ka of HA will be in the numerator and the Ka of BH plus will be in the denominator. But we'll also see those two factors of Kw cancel each other. You can work out the math. I hope you'll just take this on faith that this is the correct result. But the great thing about this result is that now we have K equilibrium written in terms of two Ka values, and those Ka values are tabulated widely. So this is something we can actually look up. We could actually get a number for a lot of the KEQs involving proton transfer between different compounds. Now let's start to summarize this a little bit. I'm going to list results on the left-hand column here for K equilibrium greater than 1. So that means we're favoring the products, in which case that means BH plus plus A minus is going to be the preferred side. On the right-hand side, I'm going to show the results for K equilibrium less than 1, which means that the preferred products are B plus the undissociated weak acid. So remember, when KEQ was greater than 1, that meant that B was a stronger base, and its Kb value is greater than the Kb value for A minus. Similarly, the opposite is going to be true when K equilibrium is less than 1. That means that A minus is the stronger base, and Kb of A minus is greater than Kb of B. Okay, so now what does this look like when we think about the Ka values? So here's some more of this table. All right, now when K equilibrium is greater than 1, let's look up at the expression for K equilibrium. We have Ka of HA divided by Ka of BH plus. So if K equilibrium is greater than 1, that means Ka of HA must be larger than the Ka of BH plus, which tells us that HA is a stronger acid. Well, that makes some sense because we're going to favor the proton moving over to B. So if HA is a stronger acid, that means it gives up its proton very easily. So we'll have that. We'll have that the Ka of HA is greater than Ka of BH plus. And I'll come down to the pKa in just a moment after I talk about the right-hand side. We'll just have the opposite results on the right-hand side. If K equilibrium is less than 1, that means the denominator, that is Ka of BH plus, must be greater than the Ka of HA. So that tells us that BH plus is the stronger acid. It gives up its proton much more readily than the weak acid HA. Now let me get down to the very last row here. In both cases, what I've done is now talk about pKa. And remember that pKa works the opposite from Ka. If Ka is large, pKa is small. If Ka is small, pKa is large. So that means if I've got Ka of HA greater than Ka of BH plus, as I do on the left-hand side, that means their pKa's must be in the other order. In other words, pKa of HA is going to be less than the pKa of BH plus. The same will be true on the right-hand side. But now let's look at how that correlates with the results we expect. If you look at the top row in this table, it shows you that the preferred products are BH plus and A minus. All right, pKa's, the pKa of HA is less than the pKa of BH plus. So in other words, in effect, the proton has moved from the lower pKa species to the higher pKa species, or it looks something like this. The same is true for KQ less than 1. although in this case the two pKa's are reversed in their roles. So in each case, the pKa tells us that the lower one is where the proton comes from and the higher one is where it goes to. So if we can remember this, that the proton always moves from the species with the lower pKa to the species with the higher pKa, all you have to do is look up those numbers in a table, a reference table, and you'll be able to tell which direction the proton will transfer. So how would this look if you were given a problem? Let's suppose you were told to find the equilibrium position for butyric acid and pyridine, a proton moving from the butyric acid to the pyridine to make a pyridinium ion and butyrate ion. Well, I can tell you right off, I'm not even going to look at a pKa table. I'm going to tell you butyric acid is an acid and pyridine is a base. So probably the proton's going to move from the butyric acid to the pyridine and favor the right-hand side. But I'm going to let you look that up on your own in a table. The steps you would follow are as follows. You would look up the pKa values for both butyric acid and the pyridinium ion. Now, you may look up pyridine in the table, but if you see a listing in a pKa table that includes pyridine, what they are really listing is the pKa of the pyridinium ion. Next, you would determine which one is larger. That tells you which one is the weaker acid. You'll then say that the equilibrium will shift toward the weaker acid. In other words, it always shifts from the lower pKa value to the higher pKa value. Finally, you would be able to theoretically find the pK of the equilibrium constant just by taking the difference between the two pKa values. We haven't talked about that much here, but it is a result that's included in the lesson. I hope this has made some sense. I've tried to take my time and explain it more carefully, but if you have any questions about it, please don't hesitate to ask.